YouTube. In this video I'm going to be running through a couple of quick examples of how you sketch trig functions. Essentially we've up until this point sketched functions that we've been given their equations and they are this form. So we say y equals some a value times, say I'm going to use sine as an example here, we could use any trig function, sine of bx, and we've also seen, loosely plus d, where d represents vertical translation. Now I'm not going to deal with any vertical translation in this particular video, but I will in future videos. But for now, I do want to note that. But we know that B controls period change, okay? So this period change right here, it also told us how many cycles, say, the sine curve will go through in a normal, amount of its period, which is 2 pi, okay? But we say period change here. The thing we want to make sure that we know for sure is this, that the period is equal to, in the case of, say, sine and cosine, 2 pi over B. And same thing with the reciprocals. So we have this in our back pockets. And then last but not least, we know that the amplitude of this graph, we say the amplitude, which sine and cosine have amplitude, no other graphs do. But we do say that it is equal to the absolute value of A. We can also say this, if A is negative, then it'll be reflected. Otherwise, we say that we're good. So I just want to make note of these things before we move forward. But basically, we're going to be graphing these just by identifying, say, A, B, and D right off the bat. So starting with this one right here, it says, let's graph y equals 5 sine 1/2 x. I'm going to go ahead and list out a few values that we're aware of. So we say A is 5. Looks like our B value, which is this coefficient of this x in here, we say B is 1/2. And then we say our D value, which we had none. I just want to point this out, though. We say it'd be plus 0. So we say D equals 0. From this, we could start to write a few things about a graph. Like, for instance, the amplitude of this would be the absolute value of 5, which is equal to just 5. So the amplitude is 5. The period, which we know is 2 pi over b, we actually get 2 pi over a fraction. This is really why I want to look at this one. People, they get worried when they see a fraction like this, but we're really going to take the first quantity, the numerator, which is really 2 pi over 1. We're going to multiply by its reciprocal. So the reciprocal of 1/2 is 2. So we get this here. We get 4 pi. Interestingly, this one is going to have a normal cycle in a 4 pi period. So let's go ahead and graph what we see. And basically the procedure for graphing this is starting at 0. We're going to go out one period length past this. So this is really easy. We're going to go up here, 4 pi. We're going to cut this in half. We'll call it half of 4 pi, which is 2 pi, and then cut those halves in half. So really simple. And we say the amplitude's 5. So I'm going to label up to 5 here. So we say this is 5. We'll go down to -5 here. So -5. And then knowing what we know about a sine curve, we say, well, first of all, would this be reflected? I suppose that's one more piece of information I want to put in here. Is it reflected? And we say yes or no. I notice that our A value is positive. So A is positive. So we say no reflection. Okay, we'll make that little note here. But basically, we're going to go ahead and draw our sine curve. So let me switch colors here. We say it starts at the ground level, goes up to its maximum, back down to ground level, down to its minimum, which is -5 this time. We say up to ground level. So a couple other things we wanted to identify here. We say domain. Remember that the domain is all reals for every sine and cosine curve. Every angle is going to have a sine or a cosine that goes with it. We can easily just look at the unit circle and say, yes, any angle would have to have some x and some y associated with it. So if that's the case, then it has all reals as an input. It goes left and right forever and ever. And then range, we say our range values are -5, less than or equal to y, less than or equal to 5. Our y values were trapped between -5 and 5. So let's go ahead and bury this number 8 down here. I want you to notice that all of its values are the same. We say A is 5, B is still 1/2, and we have a D value quite technically of 0 here, but this is cosecant. And so the thing we want to recognize here basically is this. This would be the same thing, and this looks really odd, but we say 5 times 1 over the sine of x. Okay, sorry, and basically, let me erase this here. Sine of 1/2 x. But basically, what I can tell you is this is going to be undefined wherever the sine 1/2 graph times 5 is at a height of 0, basically. So what we're going to do is this. We're just going to graph this graph, right? And let me put it in a different color. We are going to graph its reciprocal function. We're literally going to graph y equals 5 sine 1/2 x. And then we're going to go off of this graph here if we want to graph a cosecant graph. So basically, we're going to resketch the same graph. This went out to 4 pi. Cut that in half. We have 2 pi. Cut those halves in half. We're going to go up to 5. 5. We're going to go down to -5. -5 here. And we're going to sketch in this sine curve that we had associated with this. So it's basically the same curve here. But what we want to recognize is, again, I'll switch back. Let me put this in here. This isn't really the graph we're after. I'll switch back to a different color here, but when this one's at a height of 0, what I know is then the reciprocal function has to be undefined. The reason why is because the reciprocal of 0 is zero or undefined, pardon me. So we're going to drop in some asymptotes here. We're going to drop in an asymptote here, here, here. That's a very similar color. Sorry about that. Switch to more like a red. And then we're going to say, well, the reciprocal of that and the reciprocal of that would be at the same points, and we're going to go ahead and come down and draw our swoops. But basically, this is how you would draw a cosecant or a secant graph. Just draw the sine or cosine curve associated with this. So the amplitude, this would have no amplitude. Remember, by definition, the definition of amplitude is half the distance from the max to the min, and this graph here never stops going up or down, so it has no amplitude. Its period here, the period is still 2 pi over b, so 2 pi over a half, but last time we did that we got 4 pi, and we can see that easily on our graph. The domain of this, here's how you do it. You pick one undefined spot. So we say x is 0 here. I'm going to say x equals 0, and then you measure this distance from here to the next asymptote. And I notice that it goes from 0 to 2 pi, the distance of 2 pi. We're going to say 0 plus any multiple of this length right here. So k stands for just some number that we are taking times, it's an integer, that we are taking times 2 pi intervals. And then we say the range of this. Notice that our range of our red graph here was from 5 up and then from -5 down. So we're going to write this as 5, or why don't we write it this way? We say y is greater than or equal to 5 and y is less than or equal to -5. But that is how you would graph these.